Hello everyone, welcome to the last week of this course Diffusion in Solids. Today we will be starting with lecture 56 where we talk about the diffusion in glasses. So we will confine ourselves to only the metallic glasses. We will study a little bit about the glass formation and the structural relaxation and its impact on diffusion. So, let us start with talking a little bit about the glassy structure. So, glass is can be defined as a configurationally frozen supercooled liquid. What it means is that in the glass, basically the structure is like a liquid structure because it does not have an order. However, it is frozen, the configuration is frozen so that it does not flow like a liquid. The properties, the mechanical, the physical, etc. are all identical to solids. So, metallic glasses which contain for example magnetic elements such as iron, nickel, cobalt are very soft magnetic materials and have magnetic losses which are lower than those measured in any other crystalline alloys, and that is why they find a lot of application in magnetic devices. They are extremely hard and have high electrical resistivity. These glasses they do not contain lattice defects such as dislocations and grain boundaries. So, as such the glass everyone knows, we know about so many of us have seen glasses all around us, but what we are talking in today's lecture is about the metallic glass. So, metallic glass is quite different. For example, your conventional glasses are transparent, metallic glasses are not transparent. The conventional glasses are very brittle, whereas the metallic glasses they exhibit ductility. In fact, they can be deformed also by suitable techniques. So, the metallic glasses offer a lot of exciting signs and interesting properties. So, the first liquid metal alloy that was vitrified by cooling from molten state to the glass transition was gold silicon. It was reported by Paul Duvet and his co-workers. So, this is the paper in which this work was published. So, we know that basically when we say glass, if you compare with an ordered binary crystalline solid, the arrangement is not at all ordered. It is a completely disordered structure. There is no periodicity that is present in a metallic glass. So, schematically it can be shown like this. There is no order present here, and there is no periodicity that is also present. So, if I have to ask you which of these patterns belong to a glass, as I said, because it does not have a structure or a periodicity. So, this belongs to a typical crystalline alloy where there is translational periodicity, where there is a symmetry, rotational symmetry also. So, this is a XRD pattern for such a crystal, whereas amorphous material they do not, as I said before, that their structure is like a liquid. Which is completely random and not periodic. Therefore, the diffraction pattern only shows a hump kind of a feature. Now, let us talk a little bit about how actually the glasses form, thermodynamically how the glass formation happens. So, you see, for example, if you take a melt. Okay, let us take a melt which is way above the Tm. Now, conventionally when you are heating this, when you are cooling down this melt, what will happen as the melt slowly cools down, here when it comes to the melting point. So, below the melting point the melt would try to crystallize, and then if that happens, then the enthalpy or the volume will decrease drastically. There will be a sudden jump in the volume enthalpy, because you know that there is a enthalpy which will be released when liquid transforms to solid. Similarly, there is a considerable volume reduction when this transformation happens. So, when if at below the melting point the liquid is brought, then it will try to convert to the crystal, and that will lead to a decrease or in the volume or the enthalpy. However, the crystallization is basically proceeds by nucleation and growth, which requires time. Okay. So, here at the melting point, the structure of the glass, so at the structure of the melt, this is a structure which is a disordered structure. When it becomes crystalline, it attains a periodicity and a certain order. So, this requires a nucleation and a growth process which needs time. Now, suppose if you do not allow that much time, if you cool down this liquid very fast, then what happens is that instead of going for crystallization, this starts cooling down, and the volume or the enthalpy begins to decrease in a continuous manner. Now, let us say if you have cooled it very fast, then what will happen is after a certain time, let us say below a certain temperature, you will see this kind of a transition happening, and below which this becomes solid, so much so that it is not now resembles in mechanical or physical behavior as liquid, but it is glass, it is like a solid. So, this happens below what is known as a fictive temperature, which is basically derived by this kind of a construction. Now, if you had cooled the glass a little bit slowly, then you would see that the fictive temperature is obtained at a lower temperature. That means the glass formation takes a slightly bit more time to happen. Okay. So, the thing is that this range beyond which now the supercooled melt will get converted to solid, this particular range is known as the glass transformation range. So, the key to form the glass is to avoid this process of crystallization. So, this fictive temperature is a function of cooling rate. So, how fast you cool, you can see that when the cooling was fast, the fictive temperature was higher, that means you can form the glass quickly. When it is slow cooled, then the fictive temperature is lower, and therefore, you have to bring down to further temperature for the glass to form. Then there is another transition temperature which is even more widely used, which is known as the glass transition temperature, TG. So, when you heat a glass, then you will see that the glass starts to transform to a crystalline peak. So, first it goes to an undercooled liquid state, and then after reaching a certain temperature, it will start crystallizing, a crystal will start to form, and this is associated with a peak. Now, this is again, although the thermodynamics is not really the subject of this particular course, but you can clearly see that there are two transitions happening. One is here, which is known as a glass transition, that the glass is going from the glassy state to an undercooled liquid state, whereas second is this undercooled liquid is now becoming a crystal. So, for this crystallization, while you see a sharp peak, there is no such peak at the glass transition temperature. Why is that so? How do you differentiate these two? So, this is what is known as a second order transition, this is known as a first order transition. Just to tell you in very simple terms, not going into very detail. For example, when crystallization happens, there is a discontinuity in the enthalpy at the melting point. All such transitions where there is a discontinuity in the first derivative, it is known as the first derivative of the free energy. These are known as the first order transition, whereas in the glass you see that this is continuously decreasing. These are known as second order transitions. Again, the TG values are also function of heating rate used. Depending on the heating rate, you may observe a different TG. Although the TG and TF are not really identical, the differences are not more than a few kelvins. Let us see also the TTT diagram, that is the time temperature transformation diagram for glass. So, you see that for example, if you start bringing down a melt below its melting point, it requires a certain time for the crystallization to occur. So, this curve represents the start of the crystallization and this represents the end of the crystallization. That means, if you are at this temperature, let us say here, if you bring down your melt to a temperature here and hold it, then it will require this much time for the crystallization to occur. That is because the crystallization happens through nucleation and growth. So, this is the temperature at which the rate of crystallization is maximum is at an intermediate temperature, not at the melting point nor very low. So, therefore, in other words, if this is the nose where the crystallization rate is maximum, if you want to form a glass, you have to cool faster than this. Okay, so when you are cooling, you should not cool so slowly that the temperature is cutting across this, but it should be cooled in such a way that it avoids the nose completely. That means you have to quickly cool it before the crystallization can begin. And if you can cool it very fast to a temperature which is below the glass transition temperature, the melt will become a glass. Now, conventional metallic glasses, they require cooling rate of order of 10 power 6 Kelvin per second, which is extremely high. Whereas the bulk metallic glasses, not the recently, but later after once the metallic glasses were introduced, then people started working on how can we make these glasses a little bigger, and therefore people started exploring the compositions and so on. So, the bulk metallic glasses, they require cooling rate in the order of 10 to 100 Kelvin per second. And why they are called bulk? Because if you have such a slow cooling rate, that means you can also form bigger diameter glassy rods or ribbons and so on. So, there are various families of glasses, they are listed here, like soda lime silicate glass, borosilicate glass, aluminosilicate glass, amorphous semiconductors, metallic glasses, bulk metallic glasses, bulk amorphous steels, natural glasses and so on. So, there is a wide variety of glasses that are available, and each of them have different applications. There are different examples for everything. So, it tells us that the glasses are an important component of several devices which are used in important applications. So, do not think that the structure is disordered or not periodic, it is not useful. Glasses do find a lot of use. We are talking about these two categories, either the bulk metallic glass or the metallic glasses. In fact, in the metallic glasses are used in transformer cores, magnetic shielding, electromagnetic devices. Typically, these glasses contain the transition elements like iron, cobalt, nickel. And the bulk metallic glasses, for example, palladium, copper, nickel, phosphorus, or zirconium, titanium, copper, nickel, beryllium. These are the glasses which can be made in a larger diameter cross section. They are used for golf club heads, formable components and so on. Now, let us talk about what is known as a structural relaxation and its impact on diffusion. So, if you heat a glass to a glass transformation range, then it may change its property depends by a phenomena which is known as structural relaxation. That means, we are heating it below the crystallization temperature, but above the glass transition temperature. So, the structural relaxation when it happens, it leads to a more stable amorphous state. So, how much the extent of property changes, it depends upon the given material, on its thermal history, on the method of the glass production. Remember, here when we talk about the structural relaxation, we are not heating the glass to beyond the crystallization temperature, because then obviously it becomes crystals and everything will change. What we are talking about is heating the glass to the glass transformation range, which means above the glass transition and below the crystallization temperature. So, although the changes that occur in density during this structural relaxation is not huge, but it can have impact on the properties like viscosity and ductility, as well as magnetic, electric, elastic and diffusion properties. So, this is how schematically it is represented. Suppose this is as I said, this is the glass transformation range, and now for example, if you heat a fast cooled glass to temperature above this glass transition temperature, you will see that the excess volume that it had, it starts to anneal out, and the volume starts becoming decrease. So it is still not reached crystallization. Crystallization has not occurred, but the excess volume has started to come down. So this phenomena is known as the structural relaxation. If the structural relaxation occurs during the diffusion annealing, so suppose if you take a glass and you deposit a tracer and you want to study the diffusivity in that glass, but during the annealing, if the glass undergoes a structural relaxation, then that means the diffusivity will depend upon the time. So if for such a radio tracer experiment, if we still want to use the thin film solution of Fick's second law, then we have to use a time averaged diffusivity. So time average diffusivity dt average is written as 1 by t 0 to t dt dash into dt. This dt dash is the small time, t dash is the time, and dt, that is the instantaneous diffusivity any time, can be written as average diffusivity plus t times d of diffusivity by dt. So schematically it can be illustrated like this, that at any given temperature the diffusivity will decrease and it will attain a nearly constant value. If you increase the temperature, the diffusivity will increase and in the every region. Also dt decrease with time to a plateau value dr. So you see here that in this case the diffusivity is actually decreasing. Why diffusivity is decreasing? So it reaches this plateau value dr, which is the diffusivity in the relaxed amorphous state. So you can write d of t is equal to dr into t plus delta d. Delta d is 0 if you anneal sufficiently. So delta d 0 means that the instantaneous diffusivity has reached the relaxed amorphous state diffusivity. And the temperature dependence of dr is described by d naught into exponential minus delta h by kBt, where delta h is the activation enthalpy. Now during structural relaxation, excess volume anneals out and it leads to an increase in density. So the volume, excess volume, is the free volume that is present, that anneals out and it leads to an increase in density of the glass. And therefore, the diffusivity decreases on annealing treatment below Tf, because now earlier you were having a more open structure, now with increase in density it becomes more packed, and hence during the structural relaxation the diffusivities tend to decrease. So these diffusivity depends upon the thermal history and the technique of the glass production. Now here I just want to tell you some features of diffusion properties of vitrolloy 4. This vitrolloy 4 is actually an important glass forming composition, which is the composition of which is like this: zirconium, titanium, copper, nickel and beryllium. Zirconium and beryllium are the major elements, zirconium being 46.7, beryllium 27, and rest 3 are present in smaller amounts. So these diffusivities of several elements which are studied in this vitrolloy 4, what interesting feature it exhibits is that it can be split into two different linear Arrhenius regions below and above a kink temperature. Okay. So just schematically I can show that normally you would expect, so far if you see that normal what we have seen for, if there is no phase transitions and so on, we expect a linear line like this. But in the case of this particular alloy, what has been seen is that there is a transition, there is a small kink that is observed. So I will just show it in a different color. So that is to say a small change in the slope. So this I have exaggerated a little bit. Actual data, if you see, you will see that the change is a little less. But the point to take away is that there is a change in slope in the Arrhenius line. So it is represented by two different linear Arrhenius regions. So this temperature is known as the kink temperature, and this is basically the kink temperature. It corresponds to the transition between the glassy and the supercooled liquid state. So between from the glassy state to the supercooled state is what is this King temperature refers to. So, the activation enthalpies and the pre-exponential factors in the supercooled liquid state are higher than those below the King temperature. And in addition, the King temperature separating glassy and the supercooled region is higher for elements which diffuse faster in the amorphous state. So, if there are two elements which for example, two alloys, if the diffusivity of one in the glassy state is higher, its King temperature is also higher. And what has been also observed or seen in the various research works, that the kink is not related to a change in the diffusion mechanism, but it depends upon the thermal history of the material. It is basically caused by incomplete relaxation to the state of the undercooled liquid. So, that means when the glass is transforming to the supercooled liquid, the relaxation is not complete, and this is what causes a kink temperature, which leads to a change in the diffusion Arrhenius slope. Finally, let us also have a couple of words about the pressure dependence on diffusion in metallic glasses. So, pressure dependence of metallic glasses have been studied to some extent. There are two types of pressure dependence has been observed. One is that the systems with nearly zero pressure dependence, so there the activation volume is equal to almost equal to 0. This is true typically for the metallic glasses containing late transition elements and where the tracers are of similar size as the majority component. And the small activation volumes, basically what it means is that if you plot D versus P, it will almost be like a horizontal line. So, in addition, the small activation volumes, they also indicate that the defects are not involved in the diffusion mechanism, because we saw when we were talking about the activation parameters for the diffusion, when it comes to the pressure dependence, the defects have a certain volume, excess volume associated with it. Some are negative, some are positive. So, when it is almost equal to 0, it indicates that the defects are not involved in this diffusion mechanism. Then there are systems with significant pressure dependence. Their activation volumes are comparable to those of vacancy mediated diffusion in crystalline solids, and this is observed for zirconium rich cobalt ZR and NiZR metallic glasses. So, if that is the case, if you have a activation volume which is non-zero, then you may have a variation which may look like this. So, this suggests that defects are involved in the diffusion mechanism, and typically what has been observed by people. So, remember, in these kind of special materials, many a times computational techniques are used to understand the mechanisms, because it may not be possible always to perform the experiments in the correct manner. So, what has been suggested is that the diffusion takes place by thermally activated motion of collective motion of atoms. So, so that means one atom doesn't move like we saw in the conventional metallic alloys or the crystalline solids. We saw that it is the atom exchanges, one atom is involved in the exchange with the vacancy. In the intermetallics, we saw some two defects are involved. Here, what is believed is that the movement or the diffusion involves a collective motion of multiple atoms. Then only the diffusion can occur. So, these are what are known as collective mechanisms. This is possible here because of the absence of the periodicity or the lack of order, because otherwise in periodic structure these are not possible. So, here the chain like motion of several atoms occurs, and these are usually seen in undercooled liquids and amorphous alloys. So, with this we will end our discussion on diffusion in glasses, and we will talk about now the diffusion in the ionic solids, which is the last category of the important materials we will take up. So, thank you.